So I warmly welcome you, Caroline, to Researcher's Desk. It's lovely to see you here. Caroline's at Stockholm University, and she's given a great title to her talk. It tells you what it's about. Drier soils lead to warmer forests. We're all super looking forward to hearing your talk today, Caroline. What I'm going to do is after you start sharing screen, I'm going to turn my own camera off so we get a really nice recording. But I'm right there in the background, and if sound fails or anything, I'll just jump right back in. So, Caroline, a warm welcome to Researcher's Desk, of course, of which you were a part of. So, welcome to your family.
Thank you, thank you. I'm super nervous, although I should not be because you are my friends.
We are your friends,
Um,
so
so
don't be
yeah,
nervous.
yeah, and I've been teaching the last 2 days, so I should have warmed up. I will start with sharing my screen.
That looks absolutely lovely. I'm going to just turn my own camera off now. And over to you, Caroline. Welcome.
Okay, so hi everybody. My name is Caroline Greiser. I'm a young researcher at Stockholm University, like 4 years after PhD now. I'm an ecologist by training, and I'm now on my own foremost project that has to do with forest microclimate and soil moisture. And I have published one paper on that topic in the spring that got quite high media attention. So I thought like maybe I present this here too. And the title is Drier Soils Lead to Warmer Forest. And I can send you home actually at this point already because yeah, that's that's what it's all about. But maybe for those who haven't seen me or heard me presenting before, I thought like giving you a bit of a background and presenting the detailed results of that paper. So I study microclimate, and that's, to put it short, it's the climate near the ground and the climate that most organisms, including ourselves, actually directly experience. So you can imagine a sunny slope has a different microclimate than a shaded slope, or these patches of snow, they stay here. And do you see my mouse, by the way, or the pointer? Can I get like a nod or a yes?
Yes, we do.
Okay, great. So these patches of snow, they stay longer in the spring, so they melt slowly because they are shaded both by topography, but also by forest, like by vegetation. You have those, those patches of sun in the forest, and you also have microclimate edge effects in forest, which I also study. So microclimate is influenced by a lot of factors like topography, so the shape of the landscape, the terrain, but also vegetation and soil moisture, distance to coast or to other water bodies. It is important to think about microclimate because standard climate data, they are not enough, at least not for ecologists. Why is that? So you see here a weather station, and these weather stations, they basically look the same everywhere in the world. They measure the temperature of the atmosphere on open, flat fields. So they pretend the Earth is a homogeneous, flat, open surface. And that's because they want to exclude, they're designed to deliberately exclude the effects of terrain and vegetation. So you would not find a weather station in the forest. The other problem is that the standard climate maps are too coarse, so they come at a too low resolution. I have this also here. So if you look at standard weather or climate maps, the best that we had for a long time, they were downscaled up to like 1 kilometer resolution. So you have like 1 square kilometer, and that has 1 temperature value. And of course, that obscures a lot of small scale variation that is also important for biodiversity. So using those coarse maps also leads us to making wrong biodiversity predictions because we classify cells or grid cells wrongly. So, for example, you would find a species in that particular cell here, and you would then assume that it likes or prefers this type of temperature. But if you look closer, it occurs actually only in this small cold spot here. So that leads us then to wrong conclusion about the climate suitability of certain habitats. And we also underestimate the effect of human land use on biodiversity, because humans, they create and they shape the microclimate landscape due to deforestation or urbanization or something. So I have worked a lot in forests, and microclimate in forests are often buffered. So when you imagine a hot, dry summer day, temperatures are often cooler inside the forest compared to outside conditions, so compared to the weather station on open, flat ground. So we can then call this maybe the cooling function of the forest. And how do we quantify it? Well, we basically take the difference between the temperature inside the forest and the temperature outside, and then we call this the offset. I will come back to this, so remember the offset, right? So it's the difference between temperature inside and outside. I have in my PhD and also afterwards worked on the effects of forest microclimate and could show that this cooling function of the forest is also very important for biodiversity in the forest. So I've measured microclimate and landscape, tried to figure out where the cold places are and where the warm places are in the landscape and what creates them, and then how biodiversity also makes use of it. For example, in Sweden, we have cold adapted species that grow more in the northern part of the country, and towards their warm range margin, we found that the species actually inhabit cold microclimates in the landscape. So we call this then refugia or microrefugia. So those cold microclimates can provide microrefugia for boreal understory species. We have shown this both for vascular plants, for lichens, and well, that's another vascular plant, but there are also mosses inside this group. So microclimate is important for biodiversity. And then I've also been part of some other work where we try to map forest microclimate across Europe and also across the globe, and then to make future projections of forest microclimate. And it all boils down that canopy cover is super important because, of course, the canopy shades and the canopy makes cooler temperature during the day. Actually, it creates then also warmer temperature during the night, but that's another story. So canopy cover is super important, but it's not sufficient. It's not the only important factor. So the current project that I'm now working on is on soil moisture. So you have cooling in the forest due to shading from the canopy, but also due to evapotranspiration or latent heat fluxes for those guys in the room that knows that know this physics. So imagine that some of the radiation from the sun is used for evaporating or evaporating water, and that energy then is not translated into an increase in temperature. So if you have sufficient soil water, you have a strong cooling in the forest understory. If the soils then get drier, you have maybe a weaker cooling effect, and that has been shown in some parts of the world, but not in Europe. And then you can even imagine, because of like prolonged droughts or other disturbances, that you have drier soils and an opening or half open canopy. So you can end up in situations where the understory is warmer than outside the forest. So that forest actually can lose their cooling function. How do I find this out? I use loggers or sensors, microclimate loggers, so tiny weather stations that are also affordable because the weather station is actually quite expensive. And with these new instruments that are rather cheap, we can create now a lot of new data and we can ask new questions. So these small white mushrooms there were designed to measure the microclimate, or they were designed in a way that they should pretend to be like a small forest plant, and they measure microclimate in the soil and at the soil surface and a little bit above the soil, and they also measure continuously soil moisture. And those sensors we can now place everywhere in the landscape, and that's what we are doing now a lot. So I'm also part of this global network and database where we try to collect now all this microclimate data in one place. So the questions that I was asking were, where and when does soil moisture drive forest buffering? And where and when can forests lose their buffering function? And this is what we expect. So I will walk you through this graph. First, on the y-axis, we have the maximum temperature offset. So that's daytime temperature in the summer. And if you are below the line, then it's cooler in the forest. If you're above this dashed line, it's warmer in the forest compared to weather station outside the forest. So first of all, we would expect that if the soils get wetter, you have a stronger cooling effect. But that also somehow levels out because the system is energy limited. So if you add more and more water, you will eventually not have more evapotranspiration just because you don't have more whatever solar radiation. Then we also expected like some interactions with topography and canopy cover. So for example, if you have, so we looked at topographic heat load that says something about how much sunlight a place receives. So this place here, the southern slope or like south-facing slope, would receive more sunlight than a shaded north-facing slope. And because the solar energy also drives evapotranspiration, we would expect that you have a stronger relationship with soil moisture on places with more sunlight, so with more topographic heat load. And with canopy openness, we expected like but that was a bit, yeah, we could imagine different situations, but you can imagine that canopy openness also interacts with soil moisture. For example, if you have a more lower canopy openness, that means more dense forest more dense forest and more trees, so they can evaporate more water. So maybe you have like a general more cooling in those dense forests, but you also have a stronger relationship with soil moisture, for example. So these were some expectations that we had. The data that I was playing around with came from the Czech Republic. So we have deciduous forest here, more at the dry end of forests. And we had 54 forest plots. On each of the plot, we had 2 microclimate loggers, one of those small white mushrooms that I just presented, and one higher up in a tree at weather station height. So we had exactly the same height inside the forest and outside the forest. So 2 loggers per plot. And then we had 1 weather station in the area that provided the reference climate data. So how does the free atmosphere look like? So we have temperature at weather station that fluctuated up and down during the summer. Then we have the daily maximum temperature offsets, so the cooling function in the forest from these 54 plots. These are all the colorful lines here. So some are colder, some are warmer, and it goes also up and down every day. And then we have from each of the plots also the soil moisture. So now we took average soil moisture per day. And now I try to, like in statistical models, I try to link these two. I try to find out if there's a connection between the moisture that goes up and down from day to day and the cooling that goes up and down. And we used 4 years of data, summer data, so only during the warm months. And those 4 years, that's actually the figure that I wanted to, what I want to show with the figure is that the years were different. So the first 2 box plots, they show data from the weather station. So the first shows vapor pressure deficit that says something about the dryness of the air. So because you only have a lot of evapotranspiration if the air is also dry. If it's super wet and super windy and super rainy, there's not so much evapotranspiration. And thus also not so much cooling. So microclimate scientists, they hate rainy, windy weather because then you have just no variation in the landscape, I guess. So 2018 was very dry. It was very warm. 2021 was not so dry, and it was also cooler. Yeah, so this is how you read the graphs. And then, so this is the data from the weather station, and this is the data from the loggers in the forest. So here we have only like 1 data point per day, and here we have like 54 data points per day. So these are all my forest plots. And then you see like the first year was very, very dry. That was also like, and it was dry in the soil. So very low soil moisture or volumetric water content. So this is the unit here. Whereas the last year was pretty wet. And this is the offset, so how much the forests are cooling. And in the warm year, they were not cooling so much. So the more negative it is, the stronger the forest is cooling. But this is basically just summaries and no statistical analysis yet. But it's still already obvious here from the year-to-year observation that if you have drier years, you also have a weaker cooling effect of the forest. So what I did now, I used statistical models that's basically regressions or multiple regressions, where I then try to explain the offset. So how much does a forest cool? I try to explain that by the soil moisture in interaction with canopy openness and interaction with topographic heat load, and also accounting for the dryness of the atmosphere, so how the evaporative demand of the atmosphere. And the results look like this. So in very simple terms, wetter soils lead to cooler forests, or in other words, drier soils lead to warmer forests. So that's basically what this graph is showing. Again, higher soil moisture leads to stronger offsets. So this is cooler than this here. That's the general pattern that we found for soil moisture. If we look at the interaction with canopy, you of course see that the more denser canopy, so these are the dark green lines here, the denser canopy, or the microclimate under denser canopies is generally cooler. Whereas in more open canopies, you have a lesser cooling effect. Not so much of an interaction, so these lines are, they have the same slope. When it comes to topography, we found what we were also expecting. So on the shaded slopes that don't receive a lot of sunlight, the temperatures are of course cooler, but they also do not respond so much to soil moisture, and you have basically like this leveling out effect. What I was talking about, like you probably hit an energy limitation here. So if you add more water, there will not be more evaporation because there's not enough sun. Whereas on the sun-facing slopes, that's the yellow lines, you have a very strong relationship to soil moisture. So on the sun-facing slopes, the soil moisture really drives the temperatures. What I also would like to highlight here is that we actually see these cases of that forests lose their cooling function. So that's when, everything that happens above this dashed line. So that's the case when forests are warmer than reference temperature outside the forest. So what I showed here. Yeah, so what does this then all mean? If you consider the cooling in a forest as an ecosystem function, something that we care about, something that is important for biodiversity in the forest, and maybe also for forest regeneration or other things, then we can also see some threats to this ecosystem function, the microclimate buffering effect. And that comes both from climate change. So we have a change in water balance. We have projections that say that the soils are getting drier in the summer, because now we talk only about the hot and the dry season. And of course, that depends a bit on where you are in Sweden, where you are in Europe, where you are in the world. So some trends are, going towards moisture soils, some go towards drier soils. But there are changes, and there will be changes. And the other come from land use. So we do not only harvest the forest and create a very patchy landscape when it comes to canopy cover that, of course, has a direct impact on near ground temperature, but we also drain the landscape. And so we tried actively to get the water out of the landscape. And that will have also implications on the microclimate landscape, and then in turn, on the entire ecosystem. I also have, as I presented before, like I've worked on this climate refugia concept, and before or earlier I was only looking like for the cold spots, and that that was created more by topography and vegetation. But now I try to rethink that concept, and think that refugia are maybe bound to water, so places that are close to springs or close to streams or in wet depressions or so. So that is something that I would like to develop a little bit further. And then also, like, when we understand these mechanisms in the landscape, try to find these places and maybe make sure that they are preserved and taken out of management or managed in a different way. Yes, other implications were, or maybe like to sum that up a little bit, that climate change has more dimensions than temperature. There are interactions of temperature and moisture. So when it's drier, it also gets warmer, at least near the ground. And of course, if you have warmer temperature, and also you have more evaporation, that's why it gets drier. Forest biodiversity is at threat from changes in water balance, not only in temperature. And then I was also thinking about what Paul Glantz has presented recently about this humidity paradox, that now I was talking mostly about the moisture in the soil, but what if the soils get drier, but the air gets more humid? So you have like an atmosphere that doesn't demand so much evaporation anymore. So what does that do to forest microclimate? You see what I mean? So you have like maybe drier, like less water in the soil, but you also have less evaporation just because the air is more humid. So I think there will be also changes in forest microclimate because of that. So I showed you now this study from the Czech Republic and deciduous forest. I have spread a lot of loggers now also in Sweden, and I will analyze the data and see what our Swedish forest says to that, like what I find with this question, like in the Swedish forest. So I have like since 2022 microclimate network in these 2 or 3 different regions in Sweden. And that's what I'm working on basically right now, among a lot of other things. But yeah, if you are a researcher and you're interested in collaborating or like adding on a study on this in these sites, like, just contact me. So that's what I wanted to say. Thanks for listening. Some fieldwork impressions, my email address, and now I'm curious about your questions.
Thank you so much, Carolina. That was a really, really nice presentation of some super research. Thank you for being with us at Researcher's Desk.